So today I'm going to be talking to you about automated summarization of scientific journal articles. A little bit of background about me. I'm a data scientist with a particular passion for scientific literacy and education. Graduated from Columbia University with a bachelor's in biology, and while I was there, I participated in a number of research activities as well as after graduation. So I've had the opportunity to read a lot of scientific literature in my lifetime. So there are upwards of 25,000, probably closer to 30 or 40,000 different academic journals and in the biomedical sciences alone, there's now over 1 million new articles published every year, meaning 2 every single minute. And one study found that as many as 50% of published articles are only ever read by the authors, reviewers, and editors of the articles, meaning no one else is reading them. And we know that increasing scientific literacy and awareness can improve public health and really hasten innovation. So a little bit of background about the dataset I worked with. It was the Pubmed Open Access Database, consisting of 3.6 million full-text journal articles from over 15,000 journals. The earliest article was from 1780, and it goes all the way up until 2021. And the average length is about 2,000 words. So just to get a better idea for what's in that data set, you can see here the most common journals. So as expected, the top journal represented in the data set is sort of more of an open access journal in and of itself, +1, but there are also some other very common, very reputable journals, Science Reports, Nature Communications, etc. So here, this chart really illustrates the core of the problem and why we need to get better at handling all the information that we're generating. So that you can see that just in the past 15 or 20 years, the number of publications in this data set has really, really exploded, highlighting the need for better data processing and understanding of all the information that we're generating. So I mainly worked with these two transformer models, BERT and PEGASUS. So BERT was the first of its kind bi-directional encoder, meaning that it could use the surrounding context both before and after different words and phrases to get a better understanding of that context, whereas previous models had only been able to look forward to understand context of previous words. And I also worked with PEGASUS, which is built off of that similar bi-directional encoder architecture, but what it does in order to be better geared towards summarization is that it pulls out the most important sentences and then recreates them using the context of the surrounding sentences. And that model is also pre-trained on 2 very, very large data sets and then fine-tuned on some smaller data sets as well. For scoring metrics, I used a number of different ROUGE scoring metrics. So the ROUGE-N and ROUGE-2 measure the similarity of unigrams and bigrams, respectively, between the target and the machine-generated summaries. And then ROUGE-L measures the length of the longest common sequences between the target and the machine-generated summaries. And the F1 versions of the scores balance both the precision and the recall of the model, meaning that they're looking at how many of those common words and phrases are present in the author-generated summary versus how many of those common words and phrases are present in the machine-generated summary, and then sort of balancing those 2 things. So here's an example of a summary that I generated with the BERT model compared to the author-written abstract for that paper. So you can see that there are a number of common words and phrases between these 2 abstracts, but they're very much more about the specifics and the results rather than sort of the overall meaning of the paper. And so the ROUGE metrics were pretty good, but not quite within the bounds of sort of the state of the art of the industry. Then I also worked with the PEGASUS model, as I said, and here you can see that it generated a shorter abstract, but the proportion of the common words and phrases in this machine-generated abstract relative to the length of the abstract is much higher than in the BERT model, which is why it led to these much greater ROUGE scores, which are closer to within 10% of the current state of the art. And so here you can see that better pictured the relative strength of the summarization of the different models. So on the left, you have of each of these groupings, you have the current state of the art, and then followed by PEGASUS at the next highest, within about 5 to 10%, depending on the metric of that state of the art, and then followed by the BERT model, and then you'll see a baseline model, which is an untrained transformer network, which, as you can see, was far worse than any of the trained models. So I was able to produce summaries within about 10% of industry benchmarks, but they were very distinct in their results. So the BERT extractive method was much better for pulling out the real details and results of a paper, whereas Pegasus was really good at capturing that overall meaning and the importance of what was in the contents of the paper. So I hope to continue to refine the Pegasus approach, and I finished implementing it in a Flask app that would allow users to input a full text article and it would generate a machine-generated summary, and hopefully I would be able to generate those summaries in simple English to make them more accessible to the general public. So here are my references and the technologies that I utilized. Thank you very much, and feel free to reach out to me on LinkedIn or look at my code on GitHub. Thank you.